All right. Cool. Looks like we're streaming. Cool. Looks like we're streaming. Looks like we're streaming. Hey everybody. Welcome to my my coding stream where it's so far it's just been me figuring things out, reteaching myself. Sorry, let me mute this in the background. That's anyway. So it's just basically been me mostly just doing some coding, retraining and reteaching myself C++. It's been many years since I've touched that. Let me go ahead and pause streams here so I don't get any feedback. Cool deal. I think we're all set up. I wish I could, give me one sec here. I'm going to try to bring these windows over. I'm going to try to get them where I can, see if I can get this where I have a kind of a view of the chat. I'm getting set up here. I'm still learning. I got a lot going on. I apologize for that. Let me double check. Am I streaming to Rumble? Yes, I am. Okay, cool. Yeah, we're good. All right. So I'm on Kick, Rumble, YouTube, as well as what's the other one, guys? What am I missing here? Twitch, the big one, the important one. All right. I still got some background noise going on here. Oh, here it is. Goodness. I apologize for that. All right, let's get started here. All right, today, so I'm still getting echo. Hang on. What in the world is going on? Somehow this thing keeps starting itself. Okay. Cool. Silence. No feedback. No feedback loops here. Even though we do loops, we try to avoid them though as much as possible. So I'll just go ahead and get started. My name's Ian. I like I said, I've been reteaching myself C++. Basically, just quick disclaimer. I'm not an expert at C++. I've been doing software development for about 19 years, so I do consider myself an expert at software development in a variety of languages, including C++, but that was about 16 years ago that I did C++ specifically. I've done a lot and a lot too much, probably a lot of front end for many years, and that's not how I started out. I started out doing everything, just full stack databases, backends on servers, and front end work, and then I transitioned into front end work, and there's just a lot of work there, a lot of opportunities, and I just went after them. And in some ways it was cool, it was fun, and in other ways it probably hurt my career, but that's all right. You live and you learn. Although, you could argue that it was probably the right choice. Anyway, so today what I want to do is as the title hopefully indicates, I want to review some of the code I've done so far and what I've been building. I'm getting echo again. I'm going to go ahead and just close this guy out. This is not cool. Okay. I had to close that tab. So basically what I want to do is I want to get into, I've been doing putting together basically a multi-threading queue system for essentially to kind of support my kind of end goal is to have a project where basically I can use this multi-threading queue system to basically handle high concurrent operations and things going on a like an API, for example. Excuse me. So basically, that's what I've been working on, and Coroutines is a pretty new in C++ world, I guess, since version I think 20. And basically, there's libraries. You can just install a library and just start using coroutines, and they come with some. I would imagine they have. I haven't looked into this, but I would imagine they have some multi-threading support. I don't know that for sure. I decided, why not implement my own? And that way I can learn C++ while trying to learn basically all the concepts behind what I decided to go with, which is called the Chase Lev work stealing DQ system or design. And in essence, what that does is that basically, I wonder if I should use a visual here. It might not be the best, but it might actually help. And for some reason, I don't seem to... Okay, my application for that apparently is not in my start menu, and I don't even want to try... Oh, there it is. I just saw it. Where did you go, you little sucker? There it is. I just can't. I guess I'm blind, or it didn't show up or something. So in essence, I don't know if the visuals will be very good, but I'll go ahead and give it a shot. Let me see if I can turn off this like notepad kind of look. Who cares? I'll just leave it like that. Alright, I got some kind of way to draw. That's cool, that works. I don't know what you guys prefer. I think I'll do the thinner one. I'll do a slightly different color. Something that kind of shows up pretty well. Okay, so basically with basically what you have is you have basically in the Chase Lev design, the idea is you have a queue that basically basically what happens is it will push at one end of the queue, and then it will basically remove from the other end. And let me ask AI for a quick example, because I am drawing a blank. Thanks, you stupid web app. Sorry, I'm typing and it just decided to refresh while I was typing. Can you give me a visual of a Chase Lev work stealing queue? I'm gonna draw it out. I just want to make sure I get my facts correct, because I think I could just look at the code too and just see what it's doing. I'm just being lazy right now. I've been coding all day. What is it? It's actually making a diagram. Okay, that might be a minute. Let's go look. Let's just look at the code. Why not? If I go over here to my project and I look at my code, you should see in here somewhere. So it's included. Oh, this is actually kind of nice. I might actually just use this because that'll save us all some time, I think. I love this visual. I'm sorry, I have to use this. Okay, I'm just gonna use this because this actually did a good job, a darn good job, I'd say. Okay, so there we go. So basically you have a queue, right? It's basically just a vector, I think, if I'm not mistaken. But it's a fixed, specifically it's a fixed size vector, which just is a lot more efficient. There's no new memory allocations or copying around of arrays as it gets the data in the memory as it gets moved, as it grows or it gets larger. But in essence, the owner would be basically one like worker thread, let's say, and it owns the queue, right? It has this queue that's a fixed size array, and in essence, what you have is the owner is basically operating at the bottom of the the queue. It's basically pushing and popping things from the very bottom. And it also maintains, positionally, it maintains the top index as stealers take from this side of the queue, from the top. And so what happened, that's basically this diagram here. It's, you got a thief. The thief basically runs out of work, nothing to do. That's kind of funny. Clever design. So the thief, basically somebody who's out of work. It's another thread. It's out of work. And it basically says, you know, hey, I'm going to take a look at the other threads and see if there's one that has, you know, items. And then I'm going to try and I'm going to snag one off the top and not really say, you know, not really interact or say anything to the owner. I'm just going to try to snag one. And basically that enables, if one thread starts to get task saturated and it gets too much going on, that basically just enables it's just more efficient and faster. You have multi-threads that can basically operate on the same queue, and they can steal from each other, and so they can kind of, one runs out of work, that one that's out of work can then start helping other threads that are overloaded. So hopefully this visual helps. All right, so basically I like to stick to the code because for me, I prefer to just read code, and then I tend to learn more that way. So I'm going to go ahead and just jump into the code. Let me close this tab. All right. Let's go ahead and get into the code. All right, so I'm going to walk through this, starting with, let's see, I'm going to start with the DQ. I think that'll be the part that kind of, what do I have here? Let me do a quick, where's my notes? I guess I didn't even make notes for this. Okay, let's just dig in and just go through it. All right, so I'm going to open up, basically I'm going to open up, not the worker, it's going to be, the DQ is actually going to be work stealer. I'm trying to remember the class name. It might be an include so that it basically inlines all the functions where they're used. Let's see. There it is. Work stealing DQ. All right, let's go ahead and get this text kind of cleaned up so we can sort of focus, I guess. I don't think I need the includes. I don't think anybody cares too much about the includes, honestly. Okay, so basically we just kind of get in here, and if we look, if we just start out with, so I forgot to mention, it is a basically it's a circular buffer, which just basically means that the I'll just use this diagram again, but basically as it's iterating over these items, if for some reason the stealers catch up to here, and your thief is here, well, your current index position is what is this? That's 5 items. So your current index position is going to be 4. And then once you go, like, how do you continue? So what it does is it basically circles around. So the actual bottom can actually move up, and then the thief is going to be maybe down here somewhere at position 3, and this will wrap around. So that's why they call, I think that's why they call it a circular buffer. All right, so basically circular buffer, instantiate it. You get, you basically, this is just a check, make sure it's a power of 2. And if you have any questions, feel free to chat at me. But basically, in essence, you have, you know, I haven't looked at this in a while, so bear with me. We've got this kind of crazy syntax here, but we've basically got a atomic with an array. So an array, okay, let's read it inside out. So you've got a coroutine handle, basically atomic, wrapped in an atomic. So you've got an array of these atomics that contain coroutine handles. And we want to make those unique. so they shouldn't be passed around or, like treated like raw pointers. And then if you go down to, that's basically what this ends up being. That's your data. So that's the actual buffer contents. It's basically okay. So it's basically a unique pointer to an array of atomics containing, each atomic contains a coroutine handle. All right, so our capacity, that just gets set to some capacity. I think it's like, I'll look later here in a second, but anyways, it gets set to some, however many, there's some ideal numbers. I don't know, I haven't dug in on the math and how they kind of determine that. But basically you want to have like a decent capacity, imagining how many items could you possibly be trying to process simultaneously, and how quick are those things expected to kind of get cleared out of the queue, right? Some could be timers, some could be long-running tasks, and they could just sit there. However, in this system, it's kind of high concurrency, so we don't expect long-running CPU tasks, although that could be possible. You probably don't want that, but that could happen. All right, so if we get into the code here, okay, there it is. Default capacity 512, minimum 16, because I guess if it's smaller than that, it's kind of like, what's the point? Check here, create a buffer. So if you look at the, remember our buffer is a circular buffer. So it's going to instantiate that circular buffer we just looked at right here. And you kind of saw the data. The data is basically the underlying, it's an underlying array, a fixed size array. We start top and bottom both 0, so they're basically going to start here. Everything's going to be pointing to an empty basically position. We want to remove some constructors because we don't want this to just be copied around, or just set equals to some other work stealing DQ, because once it's set up, it's not meant to be moved around or copied. That's the goal behind that. Okay, so I guess let's look at the push here. So push a handle. So if you got a coroutine handle, you basically you can push that handle in, and then when you pass that, basically we're just going to get the bottom value from this using it's an atomic, so we're basically going to call load on it. And memory order relaxed, we can look at the documentation just to confirm our understanding of that, but in essence, in essence that will be it. We're kind of saying we want to get it, like just get the value, yeah, just get the value that you can find for it. It's okay if it's not currently the latest value. It's okay to be a little sloppy, I guess. And just to be clear, the value is going to be, the bottom is going to be down here, right? So we're just trying to kind of get a rough ballpark of the bottom. We get the bottom. That's also going to be a little bit faster when you're doing like extremely high performance processing. You get the bottom, and basically you don't want to tell it to synchronize with the other like cores or threads, the memory, because basically you're just kind of using it as a rough comparison, I think. And when we get down here, we'll see that, minimize that. All right, so when we get down here, we'll do a quick, let's see here. We'll do okay, so now we're getting the top. And the top is where I think the thief steals from. I think that's how I set this up. I basically followed kind of what the Chase Lev sort of approach was. Anyway, so acquire is going to say, make sure that when you get this value, make sure that there's no pending other things changing or updating this at the time that you get it. So we want to get the latest written memory value at this for top. We get that top, we subtract subtract it from the bottom, and if it's over the capacity amount, greater than or equal to capacity, I should say, that basically means that one of them has changed and gone outside of the range. Like top has gone too far top, like let's see, let me think for a second. Bottom is going to be the larger number, so basically if bottom is further out than top, then we know that I gotta think this through here. So let me think. Bottom, let's go back to our diagram. If we got bottom minus top, and if that's somehow greater than all these items in here, then that means that, yeah, that means that there's too many, that means we're just too far out. That means there's no more room, and so therefore we return false. Basically we want to then, if we don't return false, if it's not full, we basically want to store the coroutine, store it in the buffer at the current bottom position. And now keep in mind, this is the owner, the thread owner that would call push. And so it's going to basically, what am I trying to say? It's going to add to the bottom of the buffer like it's doing. So then we're going to update it and increment the bottom. And now we want to release that and make sure that others that need to get that latest value can, because the other operations might need to know about this update. Okay, so that's the push. Hopefully I won't drag this out too long, so I apologize again. So pop, we're gonna get the bottom value, and basically -1. So that means that what we want to do is just step back 1 from the current bottom, and then we want to update that. Oh, that's right, because we're removing sorry, so the owner is basically popping the bottom and then subtracting 1 from the current bottom, so that we're now pointing to D, task D in this visual. And then we want to store that, and when we do, we want to basically do a I forget what this stands for, but if we pull up the documentation again and we just go to where you can see this, so sequential, what is it going to be here? So memory order sec CST, load operation with this memory order performs an acquire operation. A store performs a release operation, and read, modify, write performs both an acquire operation and a release operation. Plus a single total order exists, in which all threads observe all modifications in the same order. Okay, consistent, sequentially consistent. And basically that's just kind of saying that, like, we want to make sure that if there's any pending like changes, things going on, we want to make sure that we get that latest value, and we basically, when we update it, we want to essentially make sure that that goes in proper order. I feel like I'm misunderstanding it right now, because I kind of was clear on the concept originally. However, the documentation does seem a little bit not very clear here. Load operation with this memory order, because we're not loading, we're actually storing. Oh, here, okay. Here, a store performs a release operation, and read, modify, write performs both an acquire operation and a release operation. Okay. So it's going to, I think, modify, write it, and then release, which will make it visible to all other places. Anyways, decrement the bottom, store it, make sure that's released and available to all other basically threads. And here what we want to do is basically just get top. If it's the current top is less than or equal to the bottom, well, let me see here. Yeah, that's correct. So that's normal. That's to be expected. If it's less than or equal to the bottom, that means it's before the bottom. And basically we can retrieve the handle from the bottom. Let's see here. Owner takes from top, stealer from bottom. A conflict can only occur when top is bottom. Basically, okay. I think this is actually backwards, but I can fix that later. But basically, okay, this is where we get into the stealer. Okay. So currently the owner is trying to pop something. And so if I go to pop and there's basically nothing, there's nothing left, because so top is equal to bottom. That's it. There's no more items. When that happens, this is kind of the cool part that I find kind of fascinating. Basically, what we want to do is we want to take top, perform a compare and exchange strong on that atomic. And so what it basically is doing is it's saying if this top matches our previously retrieved top up here using load with memory order acquire, if these are still equal, then go ahead and exchange and update the value with t plus 1. So it's going to update the top. And in that case, if it does work, it's basically, if it's successful, it will, let's see here, it'll use a sequentially consistent operation to do that. And it will basically, if it actually, the top still matches and it updates the value, that means that, so the exclamation mark, obviously that's a not. So if it fails, you'll get a false result. And basically what will happen is it will actually go, that means that you need to just go ahead and update with the latest top value. And then kind of store that and just update what top currently became, and you don't get to steal. Now, if it passes, that means that you basically in essence won the race against other threads. That, because if this compare exchange occurs like successfully, that means that your top value did not change since getting down here and executing this if statement. And so now what you can do is basically you can go ahead and you can basically, okay, so I apologize. I totally apologize. This is not the actual steal logic, but this is in the event that you are the owner thread is popping and it's competing with a thief over the same element. And in that case, if you are successful to win, then you update your value. If you don't succeed, you don't, you increment the value. Sorry, you increment the value. If you don't succeed, you just store the existing value that was already there. And just let the thief have that item. But your top doesn't actually move in that case. So anyways, return the handle. So this else statement is going to be when your top is not before your bottom or equal to it. And in that case, that could mean, because you basically decremented the let's see here. Yeah, you basically decremented B, the bottom. And then if it goes beyond, like if it's not greater than or equal to T, well, that means that bottom's now surpassed your top. They're basically converging, and so that means that they're basically that means I think that means it's empty. Yeah, so that means it's empty, and then basically you're gonna update that top value just like as if you had, kind of similarly to if you lost the race. But anyways, you update with the current T, because let's see, your T is coming from this guy, your top value. Yeah, so if it's empty, you're not racing. You don't have to worry about that. You just update your top value. Or excuse me, the bottom becomes the top. Sorry. Yeah, so anyways. All right, so that's that. The steel, this is, I think, where a little bit of magic, little funky. Okay, I'm just making sure my camera and stuff's working over here. Okay, so basically, the steal method, okay, so this is other threads will call steal. As a matter of fact, this, okay, yeah, let's keep moving with this. So the steal method, we're going to get the top value, the current top index. We're going to acquire it, so we want to ensure that we go back to our documentation. Let's see, this is a load operation. So if we go back to our documentation, a load operation with this memory or performs the acquire operation on the affected memory location. No reads or writes in the current thread can be reordered before this this load. So when steal is called, keep in mind that it will be called in the context of another thread. Another thread will be calling it, but the code itself will actually be executed on a different thread. And so basically, no read or writes in the current thread can be reordered before this load. So if there's something else trying to read or write to top, it can't happen in the current thread. And then all writes in other threads that release the same atomic variable are visible in the current thread. Okay, so the stealer's calling. Nothing else can be reordered. Let me just clarify this. Yeah, so they can't happen. So it cannot reorder reads or writes before this top.load call. And then it clarifies that basically all writes in other threads, so any threads that are actively updating that memory location, that release it, now they have to release it, that they will be visible in the current thread. So this current thread saying you can't move other like reads and writes before me, and anything that's being released that's touching or modifying top, basically I will be able to see that. So it's basically just a way to enforce that you get the latest top value. Nothing in another thread modifies it, changes it before you get to check this value. So anyways, and then we've got this kind of took me a little while to wrap my head around, but basically you've got this atomic kind of thread fence, and what that's doing is that's kind of saying that you can't reorder like this stuff above. Let me double check. I think what it means is you basically can't, sorry, yeah, let me clarify. So this top load cannot be reordered anywhere in this code like below. So this basically the compiler and the CPU can't optimize this and take this load and move it down or around. So the fence is saying that top happens first, the load of top happens first, and then we execute this stuff. And I think the reason why that's important is because if you were to just sort of like drop this down below here, something could have come along and changed top. then you got bottom, and then you're trying to compare bottom to a top that got changed. Basically got changed somewhere in between these lines executing. Then and then in the compiler tries to optimize to get top, like, later on or something, and then move this. Who knows what else it'd try to move around, but basically you just want to make sure you have top first, then you want to get your bottom. And in essence, if top's greater than or equal to the bottom, when you're trying to steal, that means that you're that means it's empty. So we want to basically take our buffer, call load on it for the current top position. So the thief is coming along trying to steal from the top. Again, I'm going to pull up this diagram because that'll solidify it. So remember, your thief comes in at the top, steals from the top. The owner thread steals from the bottom. Okay, cool. So again, we're doing this compare exchange strong. So we're basically saying, does top, the current top atomic, does it equal this expected T value, which is the top that we got up here? Actually, I'll just leave all that code here and in here for context. I'm trying to fix my mouse so it doesn't jump around. Well, that sucks. I can't really get it to lock. Okay, so basically, if top if this top atomic has not changed and it matches our expected T value, then let's increment it. And basically what that'll do is, again, we're using sequentially consistent, I believe is what that stands for. And I'm going to go ahead and just pull that up because, again, like I said, I'm trying to make sure that I get the information correct, and I also am kind of trying to train and learn, because a lot of this stuff's, there's just a lot of pieces to these atomics and how the reads and writes occur and in what sequence and what can see what, especially in multi-threading or multi-CPUs or cores, I guess is what you'd call them. But basically you've got this, let's see, let's go ahead and just read through this. A load operation with this memory. So are we doing a load? No, we're actually going to be storing or writing. So a store performs a release operation. A read modify write performs both an acquire and release. Okay, so it's going to acquire it basically and then release kind of in a single sequential operation. Plus a single total order exists in which all threads observe all modifications in the same order. Okay, so did I just close my ID? Let's see here. No. Okay, so basically it's just going to ensure that it reads release it. It's going to modify it, then it's going to release it, and it's going to do it in a very explicit, specific order. So if that fails and you get a non-truly basically return value, well, then we lost the race against the owner. That means the owner came along, popped, and this failed, and then we basically just return a null pointer, which the using code knows how to handle. Otherwise, if we won, we basically return the handle that we got. So the rest of the methods, they're all just basic meta, like buffer meta methods, I guess you could call them, to detect if it's empty, is it full, size, capacity. Nothing interesting in those. One point that I was kind of learned about as I was going along with this was, so if you use a Lignus, let's go ahead and just pull the, let's see if I can get some official C++. I'll just use AI. Of course you give me a super long answer. Okay, so why is it showing me what happened to my code? It like jumped around for some random reason. Okay. Oh, that's right. Okay, let's just go ahead and focus on the aligness part. Okay, here we go. So this is the cool part. So this is the quote-unquote secret sauce for high-performance concurrency code. So it instructs the compiler to place this variable at a memory address that in a multiple of 64 bytes. That is a multiple of 64 bytes. Okay, why 64? So basically it has to do with, yeah, CPU cache line size is 64 bytes. So if I think what it does, I don't know why it's not giving me a, see, this is why let me just go to the C++ documentation and just look up the type. AI gets like really wordy. It tries to be super smart and gives you way too much. Wow, it's been around for a long time. Okay, the alignment requirement of a type or object. Whoops. Okay, explanation. The aligness. Let me increase the font size so you can actually see that. Okay, so the aligness specifier may be applied to a class, declaration or definition of a class, declaration of a non-bit field, etc., etc. Oh, I guess I'm too far zoomed in. All right. Will have its alignment requirement equal to the strictest largest non-zero expression of all aligness specifiers. Yeah, but what does it do? Why doesn't it give me like just a explanation? What is the explanation? So it can be applied to all these things. Okay, it will have its alignment requirement equal to the strictest largest non-zero. Okay, so each object type has the property called alignment requirement, which is a non-negative number of size t, and always a power of 2, representing the bytes between successive addresses at which objects of this type can be allocated. Okay, there we go. So representing the number of bytes between successive addresses at which objects of this type can be allocated. All right, so basically if it's represented by memory addresses, right, we're basically telling it how many bytes of actual, like, it must remain basically let's see here. Yeah, so it can only be allocated to basically 64 bytes. Is that bits? I think it's actually represented by bits because we're using it. Let me just double check here. So we have an atomic of int 64. So that should be 64 bits. I can't even, with these glasses on, it's kind of hard to read with this dark theme I have. But in essence, what that does is it just says that this atomic's memory used, or the memory addresses, need to basically remain in, let me see and make sure I get this right again. Okay, so it represents the number of bytes between successive addresses at which objects of this type can be allocated. Okay, so it's basically saying that this object or this number can only be allocated in 64 successive did it say bytes? Oh, it is bytes. 64 bytes. And so I guess what this does, like under the hood, is it basically forces it to occupy the entire space of basically a single CPU cache item or line, so that it doesn't use like a partial part of a line, or a use part of a line and then try to basically essentially spread it across like cache lines, which can then lead to cores trying to basically move pieces of the cache lines around, because you might have part of it on one line and then you might have part of it on another line, and that reduces performance. And so basically by doing this, you're kind of forcing it to fit on single cache lines, and then it's more efficient, so it can basically less I forget what they call it. I think they call it cache line, I don't know, swapping or something along those lines. But kind of a weird, very niche thing that I never even dealt with before. Kind of cool to see and learn about. So I think that in essence breaks down the Chase Lev, the crux of the Chase Lev work stealing queue. You'll have like a, basically these methods are going to be called by loops. So you'll have like thread loops that will be in a loop constantly running, or technically in this case it's actually it'll loop until there's nothing left in the queue, and then it'll basically exit out, and then it'll just sit and wait idle on this epoll, basically using a Linux epoll wait call to basically sit there and wait for file descriptors to basically trigger events, and then it'll start running that queue again. It'll go back into the loop, and during that process it'll try to pop items from its own queue, and then otherwise if it runs out of items it'll start trying to steal. So I could probably just show you if you're curious. Let's see here, if we go to, okay, so so it's actually called by the worker. The workers kind of represent a thread. Called by this, I got that wrong actually. So it's actually called by the scheduler, which in turn is going to basically pick a victim ID, kind of doing some weird math here, increase the current worker ID, get some kind of a, let's see, I think this is a random number. No, excuse me, this is the actual, I think this is the actual number. Oh no, it's a random number generator. Okay, so random number divided by the count, and then you'll get some remainder, I think, and then that'll be your victim ID plus 1, and then divide by, oh excuse me, if it's equal to self, then I guess we'd try to generate it again. We increase it by 1. Basically increase it by 1, divide it again, and try to get some remainder. Anyways, pick a victim ID, and then we basically go to that worker, and then we call steal. And if you get a handle, that means you won, and then basically return that. Anyway, that's kind of the mechanism for stealing, which gets called. Now I have to look, because now I'm dying to know. Okay, so here's the loop. This is the thread loop, or the worker loop. So it's going to go through, try to process coroutines, and if it can't find one in its inbox, or one in its, I think this is the actual, this is the Chase Lev work stealing queue. So if it can't find one in the work stealing queue, and if it can't find one in the inbox, then it will resort to theft. And then basically after that, I've got this multiple producer, multiple consumer global queue as a backup for overflow. But that's not really the point of what I'm after here. This my current topic, anyways. Okay, so that is in essence the Chase Lev core kind of circular buffer queue concepts, and how they kind of make highly concurrent, like multi-processing sort of be efficient at a CPU level, so extremely fast and efficient. I would have to dig a little further to know if it's actually good for, if it could be useful for like long running tasks. That I can't say for sure. So I wouldn't venture to say that that's the case one way or another. All right, so now what I want to do is I wanted to walk through some, let's see here, how do I do this? So I kind of wanted to walk through what I thought was kind of cool. So what I was doing was I have a bunch of tests that basically test this whole, like use the scheduler, start some workers, and in essence basically go ahead and start, and then start workers, and then like it'll there. Let me pull up the test. I'll just pull it up so I can. If I can find it, hang on. Okay, let me just so what I was doing was I was running some tests, and this particular test failed. I don't know if I can find it anymore, but I'll try real quick. I'm trying to remember if it was in the scheduler, I want to say. It was one of these. It was one of these tests. I want to say it was stop empty or start stop. Probably this one. And then let me scroll up. See if I can spot it. I've got like a slew of unreadable, well, not unreadable, but a slew of text that I kind of need to try and interpret to find the test name in there. Come on, guys. Let's see. Run all tests. Oh, here it is. It's got to be this one. Wrong test. That one failed earlier. I already fixed that, but I want to show you like kind of fixing another one. Okay. So this one creates a scheduler, 2 workers, start the scheduler, and then spawn a subtask, or I should say a coroutine. And I think this will actually, return a, doesn't need to specify that, but that'll return a basically a coroutine. Which is a task of with no return type. So that's my async function that should run, get processed, and then spit out a result eventually. And then in this case, since I'm calling it directly, I guess it'll block, I think, on spawn until it gets a result and spit that result out. Now, let's run the tests. with thread. I already did this earlier, but let's just start from scratch. So if we run this with, if we run this with thread sanitizer, I did have to build it with, actually I'll just show you. Let me see how I can get, all right. All right, so basically I used CMake, but basically what I did was I had to basically give it this this sanitize equals thread flag. I forget what the -G is. I don't know if that's for global or something else. And then -01, which basically is just telling it to kind of not overly, basically a light optimization, kind of a balance of like speed and accuracy with thread sanitizer, because apparently you can kind of, I think of it like verbosity with logs. Basically you can kind of tell it how detailed you want it to be in terms of diagnosing. And I apologize, you can't even see that. Here we go. Yeah, so there's that. That's basically the command I used to basically build the tests with the fsanitize equals thread flag. So what I will do is I will excuse me, that's not actually building it. That's basically going to set up make, or create the make file for basically with, I think with the telling it to use the flag. So, and then after that, actually build it using make. So that's what I'm using. Now I have to, right now my test binary is basically in this test folder. Yeah, it's in this folder under tests. If I execute it, I get this basically exception saying that unexpected memory mapping. And apparently it has to do with Linux's, I think it's called ASLR. And basically it doesn't, it has like some kind of, so the thread sanitizer depends on like some kind of shadow memory to track operations, multi-threaded operations happening. And so when I did some searching and I asked AI, basically the recommendation was to run it with using this set arc command, and then basically passing uname -m and then -r. And then that basically allowed me to run thread sanitizer without like upgrading G++ to like a newer version on my system. But anyways, so if I run this, that runs a bunch of tests and they all passed, so that's cool. If I go up here and let's see here. So if I look, there is a warning from thread sanitizer. So basically what you get here is you get it kind of outputs like the thread identifier, what it's trying to do. It gives you an actual memory address, and then it does the same for the next conflicting read or write of the same memory location. So in this case, the main thread is also trying to operate on or access this memory location. And so if you follow the stack, it'll give you a clue as to like how that's happening. So if I look here and I go to, let's see, it's kind of hard because I like to expand my windows super wide on my actual like full screen. But if I go through here, eventually I'll find some code. Okay, here we go. So I've got worker. So unique pointer, that's an include from C++, I guess 13. That's getting into the unique pointer, like the system C++'s own, like implementations. My code, however, if you follow the stack, it's worker line 30. That's where basically this kind of conflict starts to happen with thread T41 trying to write to this memory location, and then the main thread trying to write to the same read from that same memory location. So if I look at this line, I should see what it's like, kind of what it's trying to do. As a matter of fact, I can tell just by looking at the stack. I see that there's an event loop. That's one of my classes, and it's a basically it's a unique pointer, and it's trying to do some kind of an operation on this unique pointer event loop type. And if I look at obviously same memory location, so it's probably going to be the same type, the same thing, and again you see event loop, and then you see there's like a get, so it's trying to read that unique pointer. Okay, so if I look at the main threads like kind of output here, what I'll see is I see some of my code up until here. So basically the third item in the stack, or the fourth, I guess technically. I see worker line 67 in the stack. Okay, so I got lines 30 and 67 in the same class. So if I go to the worker class and I go to starting out with line 30, okay, so basically what I can see here is it's assigning, so it's a write, just like the thread sanitizer pointed out, to this event loop type. So if I go here, if I go to it, go to definition on it, I can actually see that it is a loop, unique pointer of event loop. Okay, so that is being written to inside of this creation or instantiation of a JThread. And that happens when we try to start the worker. Now if we go down to line 67, so this, I think this would be the main thread. This is a read, and so the main thread is calling submit, and the worker apparently is trying to assign it at the same time. And so the thread sanitizer detects that there's a conflict there. And so basically for another problem I had was during stopping a worker, I'd basically have this loop ready flag, and this is an atomic boolean. So if I go back here, basically this wait is basically whenever you stop a worker, it's going to wait till the value is not false. So once this value is no longer false, then it will basically, this will block until it becomes non-false, and then it'll continue. Now the reason why I had to add this was because there was another issue where if you let's see, I'm trying to remember now, if you would basically, if you'd call stop on it would try to wake up the loop, I think, at the same time while the thread, the JThread's being instantiated and attempting to write to the loop. And so adding this wait is basically saying that wait, don't try to stop until the actual loop has become ready, in essence. So don't, until this value gets updated to true. You can't stop it. So what it does is it starts and then it tries to stop it right away. That's what was happening. So it's in the process of creating the loop, and then it just says, oh no, I'm going to stop that, and then it tries to basically access the loop even though it hasn't even finished creating it. So that was creating a race condition. In this case, if we go to line 30, we've got same line as the previous issue. So it's creating the loop, and meanwhile something over here is basically like it's already trying to spawn some kind of work, a coroutine handle, and it's basically trying to wake up the loop. Well, technically read the loop, check it for existence, and then wake it up and get started working. So basically, what I think, okay, so basically what one solution I thought of was, which was a dumb solution, was why not just add another, loop ready, basically wait, whoops, down here, like this, for example. So wait till loop ready is true, and then we can just go ahead and continue, right? Well, the problem with that is submit can get called a lot in a high concurrency situation. I guess in some cases it'd be called like a hot path. So this can get called a lot and often, and so in that case you don't really want to really be waiting, checking this wait every single submission. I mean, you could, and it might be okay, but there's actually a slightly more efficient way to do that. And what we can do is basically we can just wait till all the threads, basically block or wait until all the threads are ready, and then allow it to submit. So basically don't submit, block the starting portion until the threads are actually ready. Don't submit until then. So let's implement that. So what I want to do is update my let's see here, let me get my other windows. Okay, so if we go to our worker, let's see here, go to our worker, and what we want to add is, I think it's going to be a private variable, because I think it's just for it's just a well, let me think. No, this is actually going to be public. Yeah, so let's go ahead and just add this to somewhere. Where do I want to put this? Let's just add it. All right, let's just add it here. All right, so void wait. So it's not going to return anything. Basically what we want to do is wait until ready, is what the worker class needs to support. Okay. All right, so that gives us, that's added to the header. We don't inline all the functions for this, so we're just going to go to add it to the actual source. I'm going to try to follow this order. So I'm going to move it to after wake up, somewhere in here. Okay. Okay, so let's go ahead and define that. Wait till ready, const. And then I don't want to make this, well, maybe I could make it static. Let's see what happens if I do that. Let's just out of curiosity, let's just see what happens. Wait, did that actually make it static? Yeah, does it need to be, okay, I guess it doesn't need to be const. Okay. Oh, you know what? It can't be static because it's going to access member, it's going to have to access member variables. I apologize. All right, remove the static. False alarm. I almost said false flag. Same thing, false flag. Okay, so what we want to do is basically why is this highlight? Oh, because it's not const maybe. Okay. No, I don't want to make it static. All right, so let's do loop ready. So we're going to watch the loop and then wait. So we can wait on the atomic. And basically we want to wait till it's not false. So that means the loop is ready. I love reading logic backwards. Memory, let's see, order acquire. All right. And acquire, I think, is going to, in essence, let's go back to our C++ reference. Okay, acquire, here it is. A load operation with this memory order performs the acquire operation on the affected. Well, let me just confirm how I'm using it. One sec. Okay, so I'm using it in a wait. No reads or writes in the current thread can be reordered before this load. So all writes in other threads that release the same atomic variable are visible in the current thread. Okay, so in the current thread, no reads or writes to this can be ordered before it. And any writes to, let's see here, all writes in other threads that release this variable, they are visible. All right, so if any writes are happening, they must be ordered before this in this thread, and they must be done basically, you know, if they're, let's see, if they release it, they're visible to the current thread. So if there's writes, they release the writes to load loop ready. The no reads and writes can be ordered basically after this load. So you can't reorder, the CPU can't optimize, or the compiler, to basically perform the writes after this wait. And also any writes with release will be made visible to it. So in essence, it's just kind of saying, like, make sure that you don't do any weird optimizations. Make sure that what I get is, for this current thread, is basically the latest, you know, basically written value to it for anything that's releasing changes to it. And so that way, if something updates it to true, it can't happen, you know, optimize it and do, you know, let's see, yeah, store and then true after, because then this wouldn't see it. But since I include this, it basically kind of forces it to not be able to move this around, and it keeps it forces this to stay here in essence, this write to the atomic. Okay, sorry, I kind of belabored the point there. All right, so basically wait until ready, that's the method, and then it's going to wait until loop ready becomes true. All right, cool. So now what we can do is we can go into our scheduler start method. Do I have scheduler open? Yeah. Okay. If you look at this code, so what it does is I'm kind of reviewing this as I go along, so I apologize. So we're going to get the current running. If it's running, get out of here. If it's not running, update it to running. So now we know that this scheduler is turned on and running. And then it's going to fire off all the workers. And so now what we want to do is when the scheduler is started, what we can do is basically we can iterate over each worker and then basically force it to wait until they're all running, up and running. Then when we perform submissions, then we know that it's safe. Sorry. So when you call start, it's basically going to act synchronously. It's going to block until the workers have initialized and started their loops. That way, when you submit something, the loop has been initialized, and then you can basically pass things via submission to that loop because it's now available. And ideally, that will get rid of those. That'll get rid of those thread, basically the thread sanitization warning in this particular case, at least, for basically when in the test when you start and then you just immediately try to spawn a task, it shouldn't throw any warnings for that, because this will block until they're actually completely started. Okay, so basically for that, what we want to do is get an automatic reference to a worker from the list of workers, and then I don't know why that's underlining. Oh, it's never used. Okay, who cares? And then we'll call worker wait until ready. All right, so that should block. Okay, so let's go ahead and pull up our let's go ahead and pull up our code. Let's rebuild. All right, let's actually, I don't have to do that with the, so I don't have to run cmake. I can just run make tests, because all the files are already set up and the build is set up. Okay, now what I can do is upkey. Basically, I can run tests again with thread sanitizer. You know, I should be able to run that specific test. I don't know what flag I need to pass, but whoa, that literally fixed everything. I had a whole pile of errors before. Look at that now. Not a single issue, unless we didn't run it with thread sanitizer. Yeah, I'm a little suspect here. Okay, I was wrong. So I actually have to run cmake again. This command, I'm just going to copy paste that for now, because I don't really feel like typing out that giant flag stuff. Okay, and then okay, oh, I guess it is already built. What am I missing? There's just no way that actually Oh, what did I miss? What did I miss? Huh. Okay, set arch. Uname. I don't know what any of these flags do. I'm gonna have to look this up later. Alright, run our test binary. Yeah, it looks like it's passing. I built it with the sanitize flag, as you saw here. Sanitize equals thread. And it looks like it's just running. I guess if there's no warnings or issues, it just doesn't print anything. I'm actually gonna double check. Let's see. Yeah, it seems like, oh, okay. Well, that's awesome. That's freaking awesome. Okay, so there we go. So now you kind of get, hopefully that helps get the idea across. I feel like I kind of belabored some of the points here. Spent a little more time than I really expected on Chase Lev work stealing cues. But I hope it's overall, helpful to anybody's kind of, I don't know, if anybody's even interested in this kind of thing. But basically the kind of the thread sanitizer thing, breaking it down, kind of going through the stack, finding out where the contention is happening, and then just kind of looking at the code and kind of understanding that these things are happening in essence simultaneously. Theoretically, they're both trying to read and write at the same time. And what's kind of weird is I think the tests actually pass that way. It still somehow works, but it's basically just warning you that could lead, like these are both accessing this thing from different threads, and they're accessing it around the same time. And it could lead, it is a race condition. Like they're both just randomly, there's no enforcement of order, and therefore they could be mistaken. And so it's a really cool, it's my first time actually using it. It's a very cool tool to kind of identify that sort of thing if you're trying to do very serious multi-threading applications or coding. Cool. Thanks everybody. Would appreciate thumbs up, likes if you are checking the video out. At least that'll give it a little bit of visibility to anybody else who is kind of interested in this sort of thing. Thanks a lot, and catch you all later.